Welcome to the latest video in your Design of Experiments course. And in this video, what we're going to talk about now, we're going to start talking about how we do the analysis of standard deviation in a DOE. Now, you've already done some exercises and you've experienced one of them, which is to use the marginal means. But essentially, there are other ways to control standard deviation. So we're going to start off by just introducing those techniques. And I'm going to explain one additional technique to you, which is the idea of designing your experiment for robustness, Taguchi's method. But let's look at the methods that you could be using to control standard deviation. So your S control methods, that's what we're going to take a look at. And there's a few of them. Now, of course, method number one is use the marginal means. So this is the one that obviously I favour and the one that you've learned. So we look at the marginal means graph, we look for a nice big signal, and we go to the bottom of that signal to minimize S. So that's an easy one. The second one is that you create an S hat model. Now, those of you that have been looking at the regression table will have noticed on the left-hand side is the Y model, on the right-hand side is an S model. And we haven't been looking at the S model. But you can, if you wished, go to that side of the diagram and you can regress that model down in the same way. And you could create an S model. In reality, what you end up doing with that S model is picking a main effect and setting it to control S, because to control S, you have to fix things. And practically, if you used a model and the model said fix everything, well, clearly if you fix everything just to minimize S, I can't then use the same levers to place the process on target. So although this is a way, practically what you end up doing is this technique. So it's there, you can use it and have a look at it if you want, but it's not one that I recommend. So we haven't covered it, and we haven't covered it for that reason. The third method, which is the one we're going to have a look at in this video, is using the Taguchi robust method. And we're going to take a look at that in a second. And the fourth way is using interaction plots. Now, we haven't covered interaction plots yet. I've been saving it for later in the course. But interactions appear in models, and they do, so that they turn up as a term with a value attached to it. But you can also draw pictures of them. You saw this get used in the molding case study. So we are going to show you how to use an interaction to take a variable that the process might be sensitive to and make the process less sensitive using an interaction to do that. So that's going to be covered in a couple of special exercises. We're now going to take a look at this one, and we're also going to cover it with a case study. So the first thing we're going to take a look at is, what is robustness Taguchi's way? What's the Taguchi method of doing this? Now, what we're talking about is being robust to uncontrollables. So uncontrollable variables. So at the very start of this course, we talked about Fisher trying to optimize crop yield in a field. Now, obviously, one of the uncontrollable variables for Fisher is the weather, how warm it is, how much rainfall you get. Fisher would like the yield to go up despite that variable condition. He wants to be robust to weather. And lots of people often complain about the weather. When it's too hot, machining centres, when you're trying to machine something particularly accurately, when it's warm outside, the cast iron frame of your machine gets warmer and we get problems. Can we be robust to that? So there is a way of doing that. Now, the problem with uncontrollable variables, you can't put them in a DOE because, of course, I want the variables to be in my control. I want to go 5 at the low, 10 at the top. And I want to keep going back to 5, back to 10, back to 5. I need control to run the experiment. So how does Taguchi deal with the uncontrollable? Well, he does it in a very special way, and he does it like this. Let's take the DOE, basic DOE, 2 variables, A and B. There's the basic experiment. These would obviously be controllable things. So if this was a machining center, this could be speed and feed. Okay, they're the controllable things that we're going to test. Temperature, on the other hand, is outside my gift, especially if you're in the UK. One day we'll get a sunny day in the summer and the temperature rises above 25, 26 degrees. The next day it's raining and the temperature doesn't get above 18. That's very common in our climate. So maybe we want to be robust to that. That's very difficult to deal with. So what do? Well, you do this. Here's the data table where you're going to collect data. Now, normally what I would do with a DOE is I would collect data across the row. So I would collect sample 1, 2, 3 straight across the row, having set up that first combination. But the Taguchi robust method asks you not to do that. Here's what he wants you to do. He wants you to collect the first column of data on the coolest day possible, the coolest temperature possible. Now, in the UK, a good idea to make this happen quite quickly rather than waiting for the weather would be to do this. Why don't you come to work at 3 o'clock in the morning? I know this is hard yards, but if you really want to work this out, then you're going to do this. At 3 o'clock in the morning, we don't know what the temperature is going to be, but it's going to be the lowest. It's going to be the coolest part of the day. And then what you do is you collect a column of data. You do all 4 of those tests during that time period. Then what you do is you come back when it's a bit warmer. Let's say mid-morning, 11 a.m. We don't know what the temperature is going to be. If it's a sunny morning, it could be a little bit warmer. If it's slightly overcast, it'd be a bit cooler. But we know it's going to move on from the 3 o'clock temperature and be in a different region. What do? We collect a column of data. And then what we do is we come back at the hottest part of the day, 3 o'clock in the afternoon. Now what we know is the temperature is going to be up highest. What do? We collect another column of data. And that's the way the DOE is set up. The noise has been allowed, and the noise of these things, the noise has been allowed into the experiment, traveling this way across our data table. Okay, now what do? Now, when we do the analysis, we analyze for standard deviation using this thing. And now, if we can find a variable that turns the standard deviation down, even though noise is being allowed across the experiment, that variable will make your system robust to that noise. That's robustness. Now, you have to design the experiment like this. You have to sit down and think about the noise and deliberately design the experiment like this. Now, we're going to show you a case study that was run when I worked at Sony. It wasn't me that ran this experiment, it was a colleague. But this is a fantastic version of the Taguchi L12 with robustness built in. So let's go to the computer and we'll have a little look at this case study of the Taguchi L12 and robust data collection and how it absolutely transformed the process. Let's take a look. Okay, so before we start, I just want to introduce the process. So the process is a technique which this case study is over 20 years old. And at the time, surface mount was probably a newer technology than it is today, but surface mount is a technology that's used in the electronics industry. You can see a circuit here that's surface mount. And it allows miniaturization. It allows mobile phones to be created with lots of power. Back in the day, a reason why a mobile phone wasn't possible with so much power, it would have been the size of a desktop computer rather than the size of a small phone. But surface mount allowed for miniaturization. Now, the surface mount technique requires us to place the parts, and these little black dots here are components. So it requires us to place the component on the board, but to glue them in place. And then to wash solder through the board afterwards. So the process we are looking at is glue strength. Because if the glue doesn't hold the part on the board, the part falls off. Obviously the circuit isn't complete, and then we get rejects and problems, etc. through the process, and maybe even the customer ends up with a television with a component missing, with a feature that isn't going to work when they get the television home. So glue strength. Now you can see in the picture here, this is our measure. We are testing the torque of the glue strength. So that's our problem. I'll show you what this DOE achieved. So there is the process capability. This distribution is the before result. And obviously the blue distribution there is the after result. So a dramatic transformation in the capability of the glue strength. Now here are the variables. 7 variables at 2 levels. So of course, what DOE are we going to do? We're going to do the L12. So you can see the variables, they're very straightforward. The glue has to go through an oven, so that's what the zone 1, 2 and 3 temperatures are all about. So we're going through an oven. And the other thing we do to try and make the glue go off better is we play ultraviolet light onto the glue, and that's supposed to make the glue go off harder and therefore the torque be better. So that's one of our current solutions. So there's the process, there's the problem. What's the noise in this problem? Well, the noise in the problem is in that earlier picture. You can see it in this picture here. We have components, look, that are that size. That block ceramic is about 1 inch square, 25 millimeters square. The little black dots here, they're about 3-4 millimeters long. They're tiny little things. So what's the noise? Well, the noise is thermal mass. Because we have to make the big block ceramic stick on the board, we have to make the little chip resistor stick on the board. The other side of the thermal mass is sometimes the board is very highly populated, like the picture you see there. Sometimes the board is quite sparsely populated. So again, there's just naturally less parts on the board, so naturally less thermal mass to take the heat energy from the oven. We can't escape this. We can't escape this noise. What we need are robust settings that deal with it. So let's show you the data collection from the L12. So what we've now got is a big block ceramic. These are the big parts in a sparsely populated and densely populated part of the board. Then a chip resistor in a sparsely populated and a densely populated part of the board. All of this data was collected separately, and then what happens is we end up by putting all of this data together in one big data table and analyzing it using the marginal means. So this particular technique was marginal means only. That's all we used to do this. So an L12 with a graphical analysis and a robust element. And here's what we learned. To reduce the variability, the best supplier was Loctite. Now, this was really lucky because Loctite was the cheapest supplier. They weren't the current supplier, by the way. Horias were the current supplier. We then changed to Loctite. Another good thing, the ultraviolet light could be switched off. We were paying fortunes for the ultraviolet lamps to run this process. All of that money could be saved along with the electricity. Now that's a good thing, because what we've got to do, look, is to get zone 3 to a high temperature. And if we do that, that will reduce the standard deviation. So really the robust settings are over here. This is where robustness was discovered. In order to optimize the strength, in other words, to push that distribution as far to the right as we could, the three variables that did that were the glue dot size. So in other words, if you put more glue down, you get a stronger bond. To use Loctite again, so not only was it the most consistent glue, it was the strongest glue, and we had to get the conveyor speed down to 0.6 meters per minute. But if you look at the performance we gained, some of those settings here, by the way, some of these settings obviously are going to cost us money. But if you look at what we've learned about the process, this process is so consistent sitting here. If we allowed it to drift to the left a little bit by saving some money on those settings, we wouldn't get near to producing defects. We certainly wouldn't get close to producing the result that we've got at the moment with all this defective result here. There is no chance that that is going to happen. So we don't have to take the three variables that optimize the tension. We don't have to use those to the full. We could put a slightly smaller dot size, maybe 0.7 of a millimeter, save some money. Maybe we could take the speed of the conveyor up a little bit to 0.7, make some more product. And still we would be in a good region because of the robust settings on the left-hand side. And one final thing about this DOE, which is brilliant, is once we dialed this knowledge, once we learned this knowledge about our process, every product had the same settings, the same process settings. This was something we had never achieved before. We used to spend days trying to find unique product settings because of the unique thermal mass on the circuit board. But after this DOE, every job had the same settings. This eliminated setup time and fiddling about and development time and all kinds of things. This is the most fantastic, robust experiment. But that knowledge could only be gained by thinking the experiment through and designing the data collection in correctly to get some special kind of knowledge. Okay, now there is the case study doing that. It wasn't temperature that was the noise, it was thermal mass that was the noise. And you could see that only by sitting down, remember earlier I said spend one day designing an experiment. Why do I want you to spend one day doing this? Because I want you to think this stuff through. I want you to think, where does your system work? What challenges has your system got that maybe it's controllable? We could just put rules around it. Maybe it's not controllable. And we need knowledge to try and be robust to it. Now, this is robustness to uncontrollable variables. It's a Taguchi method, and you have to let noise come into the experiment across the data table and then analyze for S. And if you can turn S down, that is a robust setting. So that is the third way of controlling standard deviation in a DOE. In the next video, we're going to have a look at a couple of exercises where we use interaction plots to control standard deviation. But for now, I'll see you in the next video.